Hey Royals, in today's lesson we're going to work with some vectors. So we'll start with vectors in one dimension. So we'll add and subtract them along a line. And these types of vectors are called collinear vectors. And then we'll extend our understanding up to 2 dimensions by adding and subtracting vectors in 2 dimensions. So as we get started here, let's remember the parts of a vector. So if I draw a vector, remember it's just an arrow. We have the part where it points, which we call the head of the vector. And the part that does not have the point we call the tail. Now we're going to start again, as I said, in one dimension. So if I'm adding and subtracting vectors in one dimension, it really doesn't matter which vector I call my first one, which I call my second one. And it will matter when we get into 2 dimensions, but really in 1D, it doesn't really matter because we'll see it's pretty straightforward. So imagine I had a vector, and let's call this first one, I don't know, let's say 3 kilometers, and say it acts in the east direction. And I have another vector, and I have it say 4 kilometers, and it's also in the east direction. Now if I'm going to add those together, it's essentially like saying I've walked 3 kilometers east, and then I walk another 4 kilometers east. So I'm asking you, how far east did I go? And I'll call this one D1, and I'll say that that's my D1 vector. And I'll call this one my position vector D2. And we'll say my delta D will be the addition of D1 plus D2, right? So it's going to be the change of my first vector. Let's say that this was actually a displacement, delta D, and we'll say that this one was actually a displacement as well. If I'm going to add those together, you get that it's 3 kilometers east plus another 4 kilometers east to give me a total of 7 kilometers east. Now visually, you would have been able to do this as well, and you would have drawn a 3 kilometer east vector, and you would have drawn it like so. And on the end of it, you would place the 4 kilometer vector like so. Now, what we just did there was that we are going to add the tail of the second vector, in this case D2, right to the head of the first vector, which in this case was delta D1, right? And so you can see that the total here, if I was going to go from the very beginning to the very end, which we remember is this total displacement, it would be from the very beginning to the very end. Now, if the red one was 3 kilometers and the blue one was 4 kilometers, this will then be 7 kilometers, and it's in the east direction. Okay, so as you can see, it's fairly straightforward when we're dealing with one-dimensional vectors. Now, what will I do if I have a series of them? And so I've come up with a little example here with 4 different displacement vectors. And I want to just show you a strategy that we're going to use so that we don't have to actually draw them every single time. Okay, so I'm going to say, what is my total displacement? My total displacement will actually be delta D1 plus delta D2, and then plus delta D3 plus delta D4. Okay, and if I add these all together, I get 2 kilometers north plus 9 kilometers south plus 4 kilometers north plus 6 kilometers south. Now, if I said, what's my overall displacement, some of you will just naturally think, and you'll go, wait, 2 kilometers north, 9 kilometers south, so I'm 7 kilometers south. And then I add 4 kilometers north, so I'm now 3 kilometers south. And then I go 6 more kilometers south, so I get a total of 9 kilometers south. What we're going to do is, because these are acting in collinear, meaning that they are along a straight line, north and south. If we think about them, one point's up and one point's down, they're essentially along the same line. We can actually say that the south direction is equal to the negative north direction. And this will be a strategy that we can actually go ahead and use. So anytime that I have a south direction, I'm going to call it the negative north. So I say 2 kilometers north minus 9 kilometers north, because I used that idea that the negative north is my south. And then I'm going to go plus 4 kilometers north. And then I get that negative 6 kilometers north. And again, I use the idea that negative north is my south. So now everything's pointing north. Notice that I have north, 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 and north for all of my values. So it becomes just simple arithmetic at this point. 2 minus 9 plus 4 minus 6 gives me negative 9 kilometers. And again, it's still north. But how do I deal with that? Well, that is just essentially, remember, negative north is south. So that becomes 9 kilometers south. Okay, and that's what we've just essentially talked about with this picture right here. That 5 kilometers north is equivalent to negative 5 kilometers south. Okay, so we're going to use the same idea when it comes to vector subtraction. Okay, so there's 2 different methods for vector subtraction. I'm going to show you both of them. The first one is head to tail method. And that is essentially you're prepping the problem to be vector addition. And as long as you understood that vector addition is that you turn all the vectors to be the same direction, north, 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 like we did in the last problem, then this head to tail method is no different than anything that we've learned in one dimension. Okay, so what we need to remember is that displacement is that it's the change in position. So if I look at this displacement equation right here, I have that delta D is D2 minus D1. And so really what that's saying is that I have the position vector D2 minus or plus the negative of D1. Right? So I'm adding the negative of vector D1. So let's go ahead and prep our problem so that it just becomes vector addition. So that means I have to flip the direction of D1. So negative D1 is actually just negative 5.0 kilometers. In this case, it was east. And that becomes, because I have a negative and the direction, it becomes the 5 kilometers west. Okay, so now I've set up the problem so that it just becomes a vector addition problem. I know what each of these are. I know D2, I know what negative D1 is, and I'm just going to add them together. Okay, so let's go ahead and draw what we have here. So D1 was 5 kilometers west. So if I do that, I draw 5 kilometers west. And I'm just going to put a vector head on it. So delta, well, it's not delta. This is negative D1. And on the end of it, I'm going to add D2. So I'm going to have D2. So remember, it's just head to tail means that I'm adding the vector of 1 from the head of the first vector to the tail of the second vector. So I have D2. And if I think about this, remember displacements from the very beginning to the very end, we could just simply see visually that it would become 5 kilometers west plus 8 kilometers west to give me that the total displacement would be 13 kilometers west. Now we should be able to do this with algebra. So let's show us how we can do that. So delta D is going to be D2, and I'm going to just do it as if I didn't flip any vectors on us. D2 is 8 kilometers west, and I'm going to subtract 5 kilometers east. Now we're going to use that trick that negative east is west. So I have 8 kilometers west plus 5 kilometers west. And sure enough, there's my 13.0 or 13.0 kilometers west. And lo and behold, I get the same answer visually as I did with algebra. Okay, so that's the head to tail method. I'm kind of tricking the problem so that it becomes a vector addition problem, not a vector subtraction problem. Okay, so the tail to tail method is very similar, except that instead of putting my vectors head to tail, I'm putting them tail to tail, and I don't have to worry about flipping any vectors. So visually, what I mean by that. So my first vector was D1, so it was going east, and it had a length of D1, and it was 5 kilometers east. And then my second vector, now because I'm adding it to the tail of the other one, I'm going to add it straight to the tail. We'll get them so that they are exactly right on the tails. There it is. This is going to be 8 kilometers west. So D2 is 8 kilometers west. And how I'm going to calculate the resultant is that the resultant will be from the head of the second vector, i.e. the one I'm subtracting, so in this case D1. So it's from the head of the one I'm subtracting to the tail, or sorry, the head of the second one. So it goes from the head of the blue arrow to the head of the red arrow. And if I think about that, I'm going to go 5 kilometers west, and then I'm going to go 5 kilometers again west to give me delta D to be 13 kilometers west. And the algebra would be the exact same thing. So this would be the same algebra. In fact, I'll duplicate it, bring it down here, and show you the same thing. So the math would be the exact same for calculating tail to tail. So it really just comes down to how you want to visualize your problem. Okay, so up to this point, we've looked at vectors in one dimension. So now we're going to add our second dimension to our problems. Okay, so the rules that we've come up with stay the same with 2 dimensions. It's just that we have to remember now that there's going to be angles involved because I'm working with a second dimension. Okay, so I'm going to show you how to do it geometry-wise, and then in our next lesson, we'll come up with something called components, which will make it so that we don't actually have to draw out the vectors. We just simply will just be adding, subtracting values, and it will give us the overall resultant vector already. Okay, so if I look at the situation that I have now, I have a vector acting in the west direction, which is delta D1, and I have a vector that's acting in the north direction, which is delta D2. Okay, so let's go ahead and find out what the total displacement is. So the total displacement will be delta D, which will be the addition of delta D1 plus the addition of delta D2, because I'm having 2 changes in displacement. Okay, so let's draw what we actually have here. So D1, I'm going to draw in blue. So I have 12 kilometers west, and I'm going to put an arrowhead on it. So this is delta D1, and it's 12 kilometers, 12.0 kilometers, 12.0 kilometers, and it's west. And on the end of that vector, so at the end of delta D1, I take on a new path, and it's going to be 5 kilometers north. So I'm going to call this one delta D2, and it's 5.0 kilometers north. So my total displacement will be from the very beginning to the very end. So if I draw from the very beginning to the very end, the green vector here will be delta D. That's what I'm looking for. And so notice that there's now an angle associated with this. There's an angle which points from the very beginning to the very end positions. So I'm going to need to find out the length of delta D as well as the angle of delta D. Okay, so let's work through this. So delta D is equal to delta D1 plus delta D2. Now, if I was trying to find the length of delta D, I can use Pythagorean theorem because I'm dealing with 2 vectors that are 90 degrees to each other. So I could say that the length of delta D vector squared is equal to the length of delta D1 squared plus the length of delta D2 squared. And I substitute in my values, I get that this is going to be 12.0 kilometers. And I'm just going to take off the direction because the absolute value bars don't require a direction on it. So plus, I'm going to add in 5.0 kilometers, square it, And if we work through this, I get delta D, it comes out to, actually the square of it comes out to 169 kilometers squared. Taking the square root, I get delta D, the magnitude of it, of 13 kilometers. So I know the length of that green vector is 13 kilometers. The next thing I need to do is I need to add in the direction of it. I need to figure out what direction the green arrow is pointing in. Okay, so we're going to use trigonometry to find that out. I know the opposite side, which is the red vector. I know the adjacent side, which is the blue vector, which means that I can use the trig ratio of tangent to find my angle. So I can say tangent of my angle is my delta D2 magnitude divided by delta D1 magnitude. So tangent of my angle is equal to 5.0 kilometers divided by 12.0 kilometers. Tangent inverse of 5.0 divided by 12.0 gives me an angle of 23 degrees. Okay, so how do I report my overall vector? So I can say, therefore, delta D is equal to 13 kilometers. Now let's come up with the direction to it. It starts in the west direction and it rotates upwards towards the north by 23 degrees. So I start in the west direction and I rotate up to that green line. So I'm going to start west 23 degrees towards the north. Now, one thing I want you to notice is if I took this vector right here, this red vector, and I placed it on the other side. So I'm going to duplicate this vector. So let's duplicate. And I place it, oops, let's go back. And I'm going to move it to right here. And I put an arrowhead on it. And I take my blue vector here, I duplicate it, and I'm going to move it right to the tip here. You can see that no matter what path I took, if I took the blue vector, then the red vector, so I went around this way, versus if I went around that way, the green vector is going to be the same. And because of that, it forms a parallelogram, and hence that's why this way of addition is also known as the parallelogram method of vector addition. Okay, another thing I want to point out to you, and this is very, 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 very important. The angle that our resulting vector points in is always referenced to the starting location. So wherever you start from, that's the angle theta that we want to calculate, not the ending angle. I do not need that ending angle. I need the original angle. Okay? Okay, so here's another example, and this will be our last example for this lesson. Bobby the squirrel starts 4 meters east of a tree. So if I say that the tree is right here, they start 4 meters east. So let's go ahead and draw a vector 4 meters east. Boom. So that's D1. D1 is 4.0 meters east. And they end 3 meters north. So they end at D2, which is 3.0 meters north. And I want to know what is their average velocity. Now remember, velocity is displacement divided by time. So I need to find out their total displacement. That is going to be from the starting location, 4 meters east, to their final location, which is from here. So my delta D that I need to determine is this one here. Okay, so delta D in this case, I'm just going to scroll down a bit. Delta D in this case is still D2 minus D1. Right? So I'm actually going to have delta D is equal to D2 plus the negative of D1, which is going to be that their path that they will actually travel is going to be, oops, let's do it this way. They're going to go negative D1, and then they're going to go D2. I'm using head to tail method for this problem. So again, I get the same picture, and this is the angle I need to find, delta D. Okay, so let's go ahead and determine what this delta D is. Okay, so delta D magnitude squared is equal to delta D1, or sorry, D1 squared, D1 vector squared plus D2, I keep wanting to write delta, D2 vector squared, the magnitude of my displacement vector squared is equal to 4 squared, because that's the length of my blue arrow, squared, plus the length of the red arrow, so 3.0 meters, and we're going to square that as well. If I square these two terms, I get 25.0 meters squared. Taking the square root of that, I get that the magnitude is 5.0, it doesn't really look like a 5.0 meters. So the squirrels moved 5 meters, but I need to determine the direction. So the direction, again, I'm going to use tangent ratio because I have the opposite side and the adjacent side to the vector I'm looking for. So I'm going to say tangent theta is equal to the D2 vector divided by the magnitude of D1 vector. And I'm going to just add in a page here. So annotations, oh no, sorry, page manipulations. Insert, I'm going to add a page here so I can continue down the page. So I have 3.0 meters divided by 4.0 meters. I get that theta is equal to the tangent inverse of 3.0 divided by 4.0, and I get an angle of in this case 37 degrees. So let's piece this together. So my delta D vector is equal to a length of 5.0 meters, and it works in a direction that's west 37 degrees north. There's my displacement vector. I'm looking for velocity. So velocity is going to be my displacement vector divided by the time. And the squirrel does this route in 6 seconds. So that means that my velocity is going to be 5.0 meters west 37 degrees north in 6.0 seconds. So that, if I calculate, gives me 0.83 meters per second west 37 degrees north. Okay, so we've now gone through a problem that deals with vector addition and subtraction. If you have any questions or anything, please don't hesitate to reach out to me.